Welcome to the final lecture of this week, as well as for this course on NPTEL course on muffler acoustics. So, we are there in lecture, essentially lecture 60, because there is a 12-week course. So, some of the lectures so far were combined, or lecture 5 of week 12. So, the idea of this lecture is not to, the objective here is not to again get into technical discussions of sorts. This will be a relatively a shorter lecture, and what we will probably do is just have a detailed summary of the ground covered so far, that is all the topics that we have discussed in detail so far, and muffler acoustics being a a significantly a pretty wide field. A lot of things have to be covered in properly designing and coming up with a final muffler product. Lot of topics because of that could not be covered, and those things can be covered in the next advanced course on experimental and numerical techniques in muffler acoustics. So, the idea is basically to give a very holistic, very overall view of the things that we have covered so far. We have learned the principle, the concepts that we have developed, MATLAB demonstrations using planar wave theory or the 3-dimensional analysis, although only a glimpse of that was seen. Other than that, what else can be covered, we can probably have a look at it. So, let us first look at the topics that were covered so far, and things that we did. So, basically we started off, we basically started off with our wave equation. So, development of the wave equation, one-dimensional wave equation. This is summary of all the topics covered so far, summary of topics covered in this course on muffler acoustics. Okay. So, wave equation development is something that we did. The one-dimensional wave equation and D'Alembert's solution, solution. So, the topics that I am writing now is not exhaustive. Some of the topics I might be missing, but then wave equation development, D'Alembert solution, and we derived we basically stated different assumptions to derived the wave equation, and the transient solution, that is basically your D'Alembert solution, and then we did basically one-dimensional Helmholtz equation, one-dimensional Helmholtz equation, and propagation in 1D pipes in one-dimensional pipes. Okay. And then we introduced a pipe carrying mean flow, and 1D case for that we covered, and all those things helped us in later parts of the course when we did the perforated tube analysis, where we defined the aeroacoustic state variables. Okay. So, this is the we did this thing, derivation and solution. Okay. We did that, and then we did the 3-dimensional modal summation, 3-dimensional modal summation in rectangular and circular waveguides, okay, and concepts of cut-on frequency. So, this would have helped you when you in the last few lectures and also lectures of week 11, and all these things will help you in the advanced course that I might offer, and you can consider taking that as well. So, and then you have your sound pressure level, SPL, sound pressure level. the concept of that and the intensity level and sound power level, sound power level is also something that we did. And then we did acoustic impedance. It first talked about the concept of acoustic impedance and reflection coefficients we considered, reflection coefficient, and lumped system analysis we did, lumped system analysis, and inertance, compliance, all these things had helped us in understanding the the basic behavior of tubular elements or Helmholtz resonator cavity or quarter wave resonator cavities and those sort of things. And then it's only after this that we considered the concept of end correction, in pipes which are open to the atmosphere or with a flange or without a flange, and Helmholtz resonator, and most importantly we for the first time we had a look at the electro acoustic analogy and a layout and a general layout of a engine system, of an overall engine system. So we did that, and then we defined the muffler performance measure, transmission loss, insertion loss, and level difference, and kind of talked in detail under what conditions which parameter is important. Transmission loss is something that we can compute well, insertion loss is something that we can measure well, and level difference is something probably very easy to measure compared to insertion loss, but insertion loss is something that what matters to us the most, whether the thing is working or not in a given frequency range. That takes into account the source parameters, source considerations as well. And then we did a lot of lumped system analysis for a tube, lumped analysis, actually I can write it here, lumped analysis of a tube, and then the heart of the muffler, that is your heart of a muffler, that is your sudden area expansion. Sudden area expansion, that is the heart of this, of all reactive mufflers. So we did that, and then simple expansion chamber, we did MATLAB plot and analysis of that, simple expansion chamber, extended inlet and outlet muffler, which we are considering even until the last point, including 3-dimensional effects, extended outlet muffler, and this is all using MATLAB, but planar wave, 1D as well as 3D, using different models. Different models were covered, and we did lot of MATLAB analysis, and then variable area ducts, conical mufflers, and then we spent a lot of time on perforated muffler system, perforated muffler system. So this involved review of different perforate impedance expressions. This involved a review of a lot of perforated impedance expressions which is used in the literature, and then we did a simple CTR, that is concentric tube resonator, and talked about how to tune it. Concentric tube resonator is one of the most important configurations that we are considering in this course, something like this. Let me draw this guy again here. So these extensions were formed at the inlet and outlet, and they double tuned this thing. So double tuning of such systems, double tuning of such system double tuning actually using a concept of differential length to double tune it. Okay. And then we have your the effect of mean flow, effect of grazing mean flow on perforated impedance and TL performance. Okay. We did a lot of that study as well, and then we considered a cross flow configuration. I am not going to do that right now, show that right now, but basically cross flow perforated mufflers, like for example plug flow etc. Plug flow mufflers and multi-pass perforated tube mufflers, multi-pass perforated mufflers, and did advanced muffler analysis using integrated transfer matrix approach, integrated transfer matrix approach, and your network analysis of such perforated systems, network analysis, and other thing actually I probably am sort of missing here is obviously CCTR, conical concentric tube resonator, which is a straight through configuration, but we briefly had a look at that as well, and detailed development of all these things we did, but all these things was done within the category of one dimensional analysis, with the understanding that higher order modes are generated at such things, but then we are taking into account the effect of higher order modes through some end corrections which we just briefly mentioned. Okay. So, 3D analysis of such things have not yet been done, and we just did the 1D analysis, and then of course we had multiply connected mufflers, multiply connected muffler systems. Okay. Multiply connected muffler systems like Herschel-Quincke tubes, and multi-pass perforated tube mufflers using network analysis like I mentioned, and then we for the first time we did something like 3-dimensional analytical modeling of some simple systems, and analytical modeling using different approach like piston driven model, Green's function model, piston driven model, Green's function, and mode matching, and we showed that mode matching is important for systems like extend inlet and outlet, but then we really have to, if the port diameter is small, we can just consider only planar waves in the port and still we are going to get good results. And then we kind of had a very something like introduction to an introduction for a dissipative something like this kind of a muffler system. I just ran some MATLAB codes to demonstrate what was going on if I fill this up with a dissipative material. So, we covered a lot of topics, but mean flow was not by and large not quite included here. Mean flow wasn't included, but I guess what we probably could do is basically we have covered a lot of ground, but things that could not be covered because of lack of time in this course and detailed development of equations, MATLAB demonstration, some of the topics, some of these topics which have to be covered in a future course, something like numerical and experimental methods, a short course on muffler acoustics on experimental methods for muffler acoustics is basically things like numerical mode matching, of perforated muffler components, because everyone uses perforated plus dissipative muffler components, detailed analysis of dissipative mufflers like there are things like parallel buffer muffler, dissipative mufflers like for example, some of the topics that you can find on the website we could not quite cover, development of equation development, lined duct muffler, hybrid mufflers, and your lined bends, and parallel baffle mufflers, plenum chambers, lined plenum chambers, parallel baffle mufflers, and your plenum chambers, and so on. And then all this is a detailed review of the absorptive materials, some properties of that, Delaunay and Beasley's coefficients, and detailed analysis of such configurations have not quite been done, and other, because these things are used in industry. This is also used in a lot in actual applications. Other thing is, of course, your experimental things, for example, which include your impedance tube measurements, which comprises a host of large range of techniques to measure the the absorptivity coefficient. So, if you have microphone like this, microphone going in the tube like this, and you are putting up a specimen, you have a loudspeaker excitation here, and putting a specimen something like here back with the rigid cavity with air, and you are trying to figure out what the noise would be from the microphones here, and finding out the alpha absorption coefficient versus frequency, something like this. And using such a system, if you basically put a muffler here, muffler 1, muffler proper, and 2 microphones here. So, two source method using 4 microphones, that is reverse the direction of the source and get equations, or 2 load methods using transfer functions and comparison of different methods and so on. So, the detailed analysis of such a thing has not quite been covered in this course. So, numerical and experimental methods for such muffler configuration is something that has not quite been covered. And also other thing is that something like a reverse engineering, not quite reverse engineering, I would say analyzing a real time or commercial muffler which is used in automobiles, and develop and employ all the methods, 1D analysis as well as 3D analysis, to analyze the transmission loss performance of such a system, whatever it is there. But before you do that, you must also have another technique, basically a CFD, computational fluid dynamics analysis of the flow paths in mufflers. So, what it does is that it is going to show you different different path. For example, if you have a complicated muffler system like 3-pass perforated duct, something like this. So, this is your thing. This is something that you should be familiar with now. So, what happens when you have a flow going in here and coming out and all that sort of a thing? So, we basically do not know how the flow will go around. So, basically Munjal and his colleagues, his students, have developed the flow resistance one dimensional theory to give an approximate value of flow distribution through these perforated pipes as well as in the chamber, to some approximations. And especially in the perforated pipe, the flow distribution is important because that will help us to evaluate the dissipative effect of dissipative effect of perforated impedance, and using that we can sort of find out the transmission loss performance. But all these one dimensional flow resistance theory has to be corroborated by a proper CFD analysis using some commercial software. So, a detailed analysis of the flow mean flow in such mufflers is also of importance, because because such mean flow expressions can then be used in the perforate impedance expression to find out the actual real time resistance offered by the perforates for a given frequency range and for a given operating speed. So, a detailed course on these 2 or 3 topics, numerical analysis, dissipative mufflers of both the reactive, dissipative combined, experimental methods and demonstration and CFD analysis of such a thing, and then employing all these things to analyze a commercial muffler, suggest some changes to enhance the performance of such a thing, would be very handy indeed. And once we are able to do that, we will come up with a final product of how are we going to develop a commercial muffler and also large industrial mufflers. So, that is something I have not really covered. So, those mufflers are really something like 1.25 meters in cross dimension, that is diameter. Length could be 2 meters or or more, and such things are used a lot in excavation operations and stuff like that. So, a detailed analysis of such a thing is also very important. So, all these advanced topics will be covered in possibly in the later course at a suitable time, and so we have in this way we can develop a very niche area of analyzing such muffler components. So, what I will do is that I will stop the lecture here, stop the course here, and see you, all of you guys, some interested participants at some later point in future, where hopefully we have more such topics for discussion and perhaps some laboratory demonstration as well. Just like we had MATLAB demonstrations, such demonstrations can also be done on MATLAB for 3D analysis or on a commercial software, like different things are there. So, and then possibly some impedance tube demonstrations can also happen. So, all these things will be there, and till that time what I will do is that I will stop here and I will see you in the sometime in future. So, thanks a lot.